Related rates is a subject in calculus that most students have difficulty with. However, you can improve with practice. Let's get some. Number 1 says, at a height of h meters above the surface of the Earth, the atmospheric pressure in torr, I've never heard of units of torr, don't worry about it, is approximated by this equation, P equals 760 e to the negative h over 7,000. That's an exponential decay function. Its value at h equals 0 at the surface of the Earth is 760 because e to the 0 is 1. Its graph would be decreasing and concave up and have the horizontal h-axis as an asymptote. It goes to 0 as h goes to infinity. What is this reflecting? It's reflecting the reality that as you go higher in the atmosphere, like up a mountain, the pressure decreases. That's exponential decay. A plane ascends, goes up, from an altitude of 3,000 meters at 450 meters per minute. There's a rate of change. There's a derivative. At t equals 0 minutes, is the time 0 really that important? Well, that's not so clear. The question is, how fast is the atmospheric pressure outside the plane decreasing at this time? We want to know a question about a rate of change, about a derivative. Instantaneous rate of change if you want to be a little bit more precise. What's going on here? This equation is true, giving you pressure as a function of height without thinking about time effects. However, with related rates problems, you always have time involved. In this case, a plane is going up over time. It's at 3,000 meters, say right now, t equals 0, and is ascending, going up at 450 meters per minute. It's going up at a certain speed. That's a rate of change with respect to time. What you need to do is you need to realize that P and H, for this plane at least, depend on time. What I'm about to show you is not the typical way related rates is done. I will show you that way as well, but it's a way that might be less confusing at first. And that's to use function notation. Replace the P with, say, P of t to emphasize that P depends on time. Replace the H with H of t. So you get P of t equals 760 e to the negative H of t divided by 7,000. To emphasize in your mind that for this plane, both pressure and the height depend on time. Now, you don't know exactly how the height depends on time. You could assume it's a linear function of time whose slope is 450, but that's not necessarily true. And in fact, in general, it's not true. A plane doesn't go up at a constant rate. We do know its rate at a certain moment in time, but we don't know it's constant all the time. So we don't really know a formula for H of t, and therefore we don't really know a formula for P of t. But these functions, these variables, if you will, are related to each other, and their derivatives, therefore, are related to each other. And that's the next thing you do. Since you want to know a rate of change, take the derivative of both sides with respect to t. I'll write a d dt to emphasize I'm now differentiating with respect to t. But then when I write the derivatives, I'll use prime notation. I'll write p prime of t, that's the derivative of p of t. Assume these functions are nice and differentiable functions. But how do you differentiate the right-hand side? Doesn't look so easy, and in fact, I mean, how can you do it when you don't know h of t? Take a breath. You should know the chain rule by now if you're watching this video. We are going to make use of the chain rule a lot. What we have here is the composition of two functions. Say 760 e to the x, you might say, as the outside function. I know, of course, you don't see any x's, but think that way. And the inside function, x, would be what I've circled here, negative h of t over 7,000. I need the chain rule. I need to ultimately take the derivative of that inside function and multiply times the derivative of the outside function when you plug in the inside function. Now, that's a lot of words to describe what you should intuitively know goes on here with the chain rule. The derivative of 760 e to the x is 760 e to the x, right? That's a fundamental fact about derivatives of exponential functions. But now plug in the inside function, negative h of t over 7,000, then multiply times the derivative of that inside function. This is the chain rule. And the negative 1 over 7,000 is just a constant. It stays as is. We just get negative h prime of t over 7,000. Okay? And then we can simplify a little bit. You don't really have too much. I mean, 760 over 7,000 would be the same as 76 over 700. Okay, use my calculator a bit here. That would be the same, okay, 76 over 700. We could write that down. We could also reduce the fraction further to 38 over 350, or even 19 over, what would it be? 350 divided by 2 would be 175. Yep, those are all the same. So we could write negative 19 over 175 when we reduce the fraction, e to the negative h of t over 7,000 times h prime of t. It's perhaps the nicest way to write the relationship between p prime of t and h prime of t. Okay, but we haven't answered the question, have we? How fast is the atmospheric pressure outside the plane decreasing? That's p prime of t. We're at t equals 0 minutes, and I will go ahead and plug in a time 0 here. But, you know, the fact that we're calling that time 0 doesn't really matter. I mean, we could call it some other time. We don't, again, no formulas for these things, so it doesn't really matter. At this moment in time, we do have what we need to evaluate these function values. H of 0 is 3,000. That's the height at time 0. And 450 is h prime of 0. So I can plug the numbers in and get my answer. So this is going to give, let's just keep the fraction out in front, negative 19 over 175. H of 0 is 3,000, so I get negative 3,000 over 7,000, which is negative 3/7. H prime of 0 is 450. That is the rate of change we're after in, what would the units be? Torr per minute, units of pressure per unit time. Torr per minute. And it is negative. It is a derivative, which is a rate of change, and if that rate of change is negative, it means the function is decreasing. We are after how fast the pressure itself is decreasing, and the fact that the word decreasing is up there means we'll ultimately write the answer without a negative sign, because by saying it's decreasing, we're already saying it's going down. Let's go ahead and approximate this. So negative 19 over 375, 175, excuse me, I guess I already had that there, times e to the negative 3/7 power gives me this, and then times 450 gives me about negative 31.83 torr per minute. But again, the question is phrased as how fast is the atmospheric pressure decreasing? That's already acknowledging it's going down. So the final answer would not include the negative sign, about 31.83 torr per minute for the rate of decrease. Rate of decrease. Graphically, what's going on here is well, okay, we'd have to, let's not worry about it. You have to know the formula for h of t to ultimately be able to graph p of t. So that is maybe a less confusing way to do it. It's not traditional, though. It's more traditional to use Leibniz notation. In your mind, just assume p and h depend on t, and write those rates of change. dp dt equals, it's just like before, 760 e to the negative h over 7,000 times the derivative of the inside function with respect to t. The derivative of negative h over 7,000 with respect to t is negative dh dt over 7,000. So you really get in the end, the same answer. You're just not using Leibniz notation here. And you might say it is a little quicker to do it this way. Then you'd plug in the same numbers, and you get the same answer over here as before, okay? With the rest of the problems, we will do it the traditional way with Leibniz notation. The rest of the problems that we do will have a geometric nature to them involving right triangles, so we'll use a lot about right triangles, both the Pythagorean theorem and trigonometry. Number 2 says a rectangle has one side of 10 centimeters Evidently that stays fixed, and that's confirmed as you read the next of it. How fast is the diagonal of the rectangle from one corner to the opposite corner changing? That's a rate of change, a derivative. At the instant, is it t equals 0 or t equals something else? It doesn't matter. When the other side is 8 centimeters, and evidently that other side is increasing, getting longer at 4 centimeters per minute. So there's a rectangle. One side evidently is fixed, not changing at 10 centimeters. The other side, this side, is getting longer. This rectangle is growing. Can a rectangle grow? Well, it depends on the application, okay? You know, if it's a screen coming down or something, that's like a rectangle growing. We're ultimately interested in how fast the rate of change of the diagonal, say from the lower left corner to the upper right corner, or vice versa from the upper left to lower right, is changing at a certain moment in time when this side is changing and happens to be 8 centimeters in length. Now, this is the trickiest part right here. Don't label this side with the 8 centimeters, okay? Don't do it. It's changing. Label it with a variable, like y, say, since it's in the vertical direction. Don't label it with 8 centimeters. That's the most common mistake here. This is a right triangle. We're interested in how this diagonal length is changing. It's not constant either. Don't label it with a certain number. Label it with another letter, like, oh, how about z? These are functions of time. Again, with related rates, the quantities that are related are functions of time. That's assumed. We're assuming this rectangle is getting bigger. It's getting taller over time here. And we're interested in the instant when the rate of change of y with respect to t is 4 centimeters per minute. But z is changing too, and that's what we want to find. How fast is the diagonal changing at that moment in time? What's an equation relating these variables? The Pythagorean theorem gives it to us. The square of the length of the hypotenuse is equal to the sum of the squares of the other two sides. So z squared equals y squared plus 100. I could call this z of t. I could call this y of t. It's just not traditional to do so. But I still do assume in my mind that these depend on t. I differentiate with respect to t, and I'm also assuming they're nice functions of t. And I need to use the chain rule. When I differentiate these with respect to t, I don't get 0. Z is a function of t. It's the inside function in the expression z squared. The chain rule says the derivative of that will be 2z times dz dt. If it were z of t, I'd write 2 times z of t times z prime of t, okay? These things are assumed to be functions of t, so I don't get 0. Same kind of thing happens over here. The 100 is an honest-to-goodness constant. It differentiates to 0. The y squared differentiates to 2y times dy dt. The derivative of the outside function, plug in the inside function, in both cases, z there and y there, times the derivative of the inside function, dz dt on the left and dy dt on the right. I used the chain rule twice here. What do we want to know? How fast is the diagonal, this length, z, changing at this instant? We want to know dz dt. That's the unknown rate we want to solve for. You could plug the numbers right away, but you also can solve explicitly for dz dt in terms of z, y, and dy dt. Divide both sides by 2. The 2's divide out. Y divided by z is, well, the fraction y over z, and the dy dt stays as is. This is an equation relating the rates of change of dz dt and dy dt. It doesn't matter that we don't know explicit formulas for y and z as functions of t. It just doesn't matter in the way these problems are phrased. So we're at a certain moment in time now when the other side happens to be 8 centimeters, y does equal 8 at this moment in time. And at this moment in time, dy dt is positive 4 centimeters per minute. So to solve the problem now, plug the numbers in here. Maybe I'll use the vertical evaluate at notation to emphasize I'm plugging in y equals 8, dy dt equals 4, and there is one other thing to find before I can plug things in. I need to know what z is. Well, that just comes from the Pythagorean theorem. This relationship between z and y works no matter what t is, and in particular at the moment in time when y happens to be 8 centimeters. when y equals 8 centimeters, z will be, well, z squared will be 8 squared plus 100, 164. So z itself will be the square root of 164. That's not a perfect square, but does it simplify? I mean, you can simplify it if you want, or you don't have to. 164 is divisible by 4. 164 divided by 4 is 41. So you'd have square root of 4 times square root of 41. Square root of 4 is 2. If you like simplifying radical expressions like that, go ahead and do it. But what really matters is what it is approximately equal to. Take the square root of 41 and multiply by 2. This is approximately 12.80625 centimeters, say. We'll round further at the very end. So that's the last value of z that I plug in about, well, let's go ahead and plug it in an exact form, 2 square root of 41. If you're after the exact answer, use this formula. Y over z is going to be, y is 8. Z is 2 square root of 41 times dy dt. That is 4 at this moment in time. 8 divided by 2 is 4. 4 times 4 is 16. It looks like I get 16 over square root of 41. That's fine for an answer. You don't have to get rid of radicals in denominators. It's not like dividing by 0. It is allowed. However, you could rationalize the denominator if you wanted to. This is the same as 16 times the square root of 41 over 41. Either way you do it, it'd be good to approximate it. So 16 times the square root of 41, whoops, is that. Divide that by 41. This is approximately 2.499, say. Or maybe I should round that to 2.50. About 2.50 centimeters per minute. Okay, so at that moment in time, that's how fast y is increasing at that moment in time. Z is increasing at a smaller rate. Does that make intuitive sense? I think so. As this rectangle gets bigger and y is increasing at a certain rate, it should make some intuitive sense that z is not necessarily increasing as fast, partially because it's tied to the fact that this leg of the triangle is fixed. It's not changing over time. So I think this does make sense. Number 3 is a dreaded car traveling problem. Car A is driving east to the right of the paper here toward an intersection. So let's start drawing something here. Here's the intersection of two roads. Intersection is what that says. That's an O. Car B has already gone through the same intersection and is heading north, going up in the paper here. At what rate, derivative, is the distance between the cars changing at the instant when car A happens to be 40 miles, traveling at 60 miles per hour, mph means miles per hour. Car B is 30 miles from the intersection and traveling northward at 70 miles per hour. So we'll find that rate. Are the cars getting closer together or farther apart? Could it be one or the other? Yeah, it does depend. I mean, if car A was pretty close to the intersection, but car B was really far away, it seems intuitive that their distance is growing over time. On the other hand, if car B is not very far away from the intersection and car A is kind of far away, it seems like their distance would be decreasing over time. Think about it. Let's go ahead and draw car A here. A is right there, and it's moving eastward. If I call this, if I call this total distance here x, that's the distance A has to go eastward to get to the intersection. X is changing over time. In fact, since A is moving to the right, x is decreasing. dx dt is negative. And car B is up here, say. That's car B. Let's call this distance y. And again, it's important. This is, again, the most common place people make mistakes. It's important to use variables at first and not particular numbers. X and y depend on time. They're not constant. We are thinking about what happens at a certain moment in time, but the actual moment itself is irrelevant. We're interested in the distance between A and B. Hey, let's call it z. This is another right triangle problem. We'll need the Pythagorean theorem again. But this time, both legs of the triangle are changing. There's really three related quantities here that all depend on time. Z squared equals x squared plus y squared. No constants there. We once again differentiate with respect to t. I'm writing the d dt, but you wouldn't have to. Just to emphasize that, and I need the chain rule in the same way with each one of these terms. I'll get a 2z times dz dt equals 2x times dx dt plus 2y times dy dt. We want to know dz dt. That's the thing we want to know. That's what we want to find. Divide everything by 2 and divide everything by z, and you'll get dz dt is x times dx dt plus y times dy dt all over z. That is an equation that gives you the rate of change of z with respect to time in terms of x, y, z, dx dt, and dy dt. Of course, z could also be replaced by the square root of this thing, so I get rid of the letter z. Let's go ahead and do that. It's not necessary to do. I mean, I will need to use this equation to solve for the value of z at this particular moment in time. But I also could replace it with the square root of x squared plus y squared. Now plug in your numbers. Wait until the very end to plug in the numbers. That's another common mistake, is to plug them in too early. So dz dt at the moment in time when car A is 40 miles from the intersection, so x happens to be 40, dx dt is 60, x equals 40. I am thinking of x as a distance here. This is a distance, not as an x coordinate, not a negative x coordinate. So that's a little bit subtle. That will mean dx dt is negative here. Instead of, if it were just an x coordinate that it was already negative, then dx dt itself would be positive because the x coordinate would be increasing. Lots of tricky things going on. dx dt is 40, or x is 40, excuse me. dx dt, careful, is 60. That's how fast the car is traveling, but dx dt is negative. It's decreasing. If I think of it as a distance. dx dt is negative 60. Y is this moment in time, b's distance here, it is 30. I'm evaluating at all these numbers here, and dy dt is how fast y is growing. And since b is going to the north here, y is increasing. Y here is both a distance and a y coordinate because it's on the positive side of the horizontal axis. So dy dt is 70. So plug in all those numbers. What do we get? We get 40 times negative 60 plus 30 times 70 all over the square root of 40 squared plus 30 squared. 40 times 60 is negative 2400. 30 times 70 is positive 2100. This is going to be a negative quantity here for the rate of change of z with respect to time. 40 squared is 1600. 30 squared is 900. 1600 plus 900 is 2500. Square root of 2500 is 50. Looks like we get negative 300 over 50, which simplifies to negative 6. What are the units? Units of distance are miles. Units of time are hours. This would be miles per hour. I could write mph, but I also can write miles per hour. So negative 6 miles per hour seems to be the answer here. At this moment in time, that's how fast, that's the rate of change of z with respect to time. It's negative, so z is decreasing at this moment in time. So they are getting closer and closer together. Getting closer together because this is negative at this moment in time. Again, there'd be another moment in time later, say, where A is pretty close to the intersection and B is way up here, where it should be intuitive that the distance is increasing over time. So these are not constant rates. We only plug in numbers at the end. Number 4 involves yet another right triangle drawn for us here, and is a pretty wild problem, pretty far out and interesting when you think about it deeply. Doing what we're asked for is pretty straightforward, although trig functions are going to be involved now. But thinking about the conclusions of what happens here are pretty mind-blowing in this kind of problem. We've got a lighthouse 2 kilometers from a long straight coastline. That's the shore right there. The beam of light makes a 1 full rotation every 10 seconds. So this is a lighthouse out to sea there on some small rock island or something like that. And that light is rotating over time. Or maybe this is the land up here and the water's down there. I suppose it could be that way too. The light is rotating over time. 1 full rotation every 10 seconds. 2 pi radians every 10 seconds. d theta dt would be 2 pi over 10 or pi over 5 radians per second if you want to know that right away. Our goal is to find the rate of change, and that's a constant rate of change, by the way. It's assumed even though it's not stated. Find the rate of change of the distance of the spot of light from the point O with respect to the angle theta at the moment in time when theta is pi over 3 radians, which is 60 degrees. Once again, don't say theta equals pi over 3. Theta is changing over time. It's increasing over time if I think of this as a positive angle direction and the rotation of the light beam being counterclockwise. We need to think about how fast is the spot of light moving away from O at that moment in time. Let's call this distance x. I can think of it either as a distance or an x-coordinate here in this picture. You would get the same answer either way. I don't want to use the Pythagorean theorem here. I want to think about relating theta and x. I need trigonometry. So ka toa, with the right triangle, sine is opposite over hypotenuse. For this angle, that would be x over the length of the hypotenuse. Cosine is adjacent over hypotenuse, 2 over whatever the hypotenuse is. Tangent is opposite over adjacent, x over 2. Oh, we don't have to find the hypotenuse here. We can just use the tangent. Tangent of theta is x over 2. Equivalently, x is 2 tan theta. Now here you actually could figure out a formula for theta as a function of time if you assume, as we are implicitly assuming here, that the rotation of this angle is at a constant rate. Theta would be a linear function of t. But once again, we don't have to make that assumption, or we don't have to use that assumption at least, to do the problem. I'm once again going to differentiate with respect to t on both sides. The derivative of x with respect to t, assuming x is a function of t, is dx dt. On the right, the derivative of tangent is secant squared. I need the chain rule. I'm plugging theta into that, then multiplying times the derivative of theta with respect to t, d theta dt. If you didn't know it already, secant is the same as 1 over cosine, so this is the same as 2 times d theta dt over cos squared theta, which really means cosine of theta, quantity squared. Find the cosine first, then square it. And this is an equation relating the rate of change we're interested in relation to the value of theta and the value of d theta dt. Now I can plug in the numbers. At this moment in time, theta happens to be pi over 3, and d theta dt, I already said that verbally what that would be. Let's write it over here. D theta dt is 2 pi radians divided by 10 seconds, which simplifies to pi over 5 radians per second. Okay, plug the numbers in here. dx dt, when theta is pi over 3, which is 60 degrees, but you want to use radians in calculus, and d theta dt is pi over 5, gives 2 times pi over 5 divided by the cosine of pi over 3 quantity squared. I could put the square there. For emphasis, I'll put it outside. That's what this notation means. Cosine of pi over 3, cosine of 60 degrees, is 1/2. This is a 1/2 quantity squared, which is 1/4. And dividing by a fourth is the same as multiplying by 4, so we ultimately get 2 times 4 is 8. 8 pi over 5. Units of x is a unit of distance, kilometers. Units of time is seconds. This would be in kilometers per second. What is that approximately? It's pretty fast. 8 pi, 8 times pi divided by 5 is approximately 5.03 kilometers per second. This location on the shore is moving to the right at this instant in time very rapidly, a little over 5 kilometers per second. I think that's probably faster than a plane would go. That's supersonic, really fast. And here's the weird thing about this problem. I mean, this is the answer. This relationship here implies that as theta approaches pi over 2, 90 degrees, where the cosine is 0, it says dx dt approaches infinity. But wait a minute, is that possible? Wouldn't that break the speed of light? Ooh, what in the world's going on here? As theta increases towards pi over 2, an angle like this distance is going off to the right, ultimately, in the end, effectively like infinitely fast, faster than the speed of light. How can that happen? I don't know that I have the definitive answer to how that can happen, but it's kind of mind-boggling, and you could certainly think about it. I mean, there's the relationship. There's also the fact that the beam of light, technically speaking, needs to travel very far once theta is close to pi over 2 anyway. And if you're really far away, you wouldn't even see it because it would be too dim because of, air, especially if there were fog, for example, not allowing you to even see this spot of light. So there's all sorts of complications going on here, but kind of interesting to think about anyway. Our last problem involves a cone, a three-dimensional object, instead of a triangle. However, in solving the problem, we'll still need to use triangles, and in fact, similar triangles, it turns out. This cone is a coffee filter, so I guess the cone should be drawn something like this. Draw a circle for the top and the sides going down like this. This entire coffee filter has a radius of 8 centimeters and a height, depth of 12 centimeters. This is going to be 12 centimeters here, the entire thing. And we're assuming water is dripping out into a coffee pot, say. Maybe there's coffee grounds in there, but it's the water that's been stained by the coffee, so to speak, dripping out at the bottom at a constant rate of 2 cubic centimeters per second. Is that realistic? Does that really happen? I don't know, but for the sake of doing the problem, we're assuming that. Part A, if the filter starts out full, so the water is up to the top, how long does it take to empty? That is a problem related to rates, but it's not a related rates problem, pun intended. There's nothing fancy we need to do there other than find the volume of the water when it's full and divide that volume in cubic centimeters by the rate at which the volume is decreasing, 2 cubic centimeters per second. So when full, the volume of a cone, remember, is 1/3 pi times r squared, which in this case is 8 squared, times the height, which is 12. We can do a little cancellation here. The 3 cancels with the 12 to give 4. 8 squared, 64. 4 times 64 is 256. 256 pi cubic centimeters is the actual volume of this, and that is approximately 256 times pi, 804.25 cubic centimeters. Okay, I'll keep that number with more decimal places on my calculator. So that's the answer to part A. Oh, not quite, excuse me. That's how the volume. Now, time to empty is that volume, 256 pi, divided by the rate at which the volume is decreasing. Think of it with the positive sign, divided by 2. This is in cubic centimeters. This is in cubic centimeters per second. The cubic centimeters ultimately do divide out. 1/seconds in the bottom becomes a second on top. 128 pi seconds. Numerically, divide this by 2. You're going to get approximately 402.1 seconds. How many minutes is that if you're interested? 60 seconds in a minute, so it's 6 minutes and about 42 seconds. 6 minutes and 42 seconds. It's how long it takes to empty. Let's leave the 256 pi in my calculator. I think I might need it later. Maybe. Part B, this is the answer to part A. How long does it take to empty? Part B, find the volume of water in the filter when the depth is h centimeters. Wait, we don't know h. It's okay. The purpose of this problem is to find the volume as a function of h. So the water is going down. It starts off full. The shape of the water, I should probably use blue here instead of red, huh? The shape of the water is still a right circular cylinder here. But now we're calling this distance here h. V is a function of h. Here's where we'll need similar triangles. Let's call this distance r. If you look at this picture, there's two right triangles here, that one and this one, that are similar to each other. Not only do they have a right angle, they also share a common congruent angle there and the same angle down there. They are similar. Similar triangles, for part B here, similar triangles implies that the ratio of r to h is the same as the ratio of 8 to 12, which is 2/3. Evidently, by the way part B is phrased, we want to find v as a function of h, so we should probably solve this for r as a function of h first. R is going to be 2/3 h. And therefore, to find the volume as a function of h, use the same formula as before. V is 1/3 pi r squared h, which is 1/3 pi r, replace r with 2/3 h. That's got to be squared, then multiplied by h again. 2 squared is 4, 3 squared is 9, times another 3 is 27. Looks like we get 4 pi over 27 h cubed is the volume as a function of h. That is the answer to part B. Final part is the related rates part. How fast is the water level falling? The word falling emphasizes we know this rate is negative. The derivative is negative, and therefore the final answer, since we have the word falling in there, will be a positive quantity representing h decreasing as a function of time because of the word falling, when the depth is 6 centimeters. So I need to take this equation from part B, assuming v and h are dependent on time, differentiate both sides with respect to t. dv dt equals, with the chain rule on the right, we bring down the 3. 3 divided by 27 is 1/9. I get 4 pi over 9 h squared times dh dt. This one's a little different in that we want to know how fast it's falling, so we should solve this for dh dt in terms of dv dt. We don't use the equation as is, though I could plug the numbers in right now. I don't have to. Looks like dh dt would be what? 9 over 4 pi h squared in the bottom times dv dt. And I could put that dv dt up in the top of the fraction as well. So dh dt, this is going to be a negative quantity, is 9 over 4 pi h squared. We're at the moment in time when the depth is 6 centimeters, so I get a 6 squared down there. dv dt is negative. The volume is going down over time. And we're assuming it's a constant decrease, rate of change for the decrease in volume of 2 cubic centimeters per second. So dv dt should be -2. We use that fact from before. So this simplifies to what? You can cancel the 2 there with the 4. -9 over 6 squared is 36 times 2 is 72. 72 pi. Don't forget about my pi there. This does simplify a little bit. 72 is divisible by 9 to -1 over 8 times pi. This would be in centimeters per second. It's not the final answer, though. should probably approximate it. I also, in the end, should get rid of the negative sign, once again, because the question says how fast is it falling, and the word falling would mean get rid of the negative sign here. So this is approximately 1 divided by 8 times pi, 0.0398. This is dHdt, but not the final answer to the question. How fast is h falling at this moment in time with the word falling in there? Means we take the absolute value of this, it's approximately positive 0.0398 centimeters per second. And what, there's like 10 millimeters in a centimeter, if I recall correctly. This is the same as 0.398 millimeters per second, for example, which is very small. The water level is not falling very fast. Thanks for watching.